This is Dr. Sanjay Kumar Sahu. Welcome to the video lecture 2 of Module 1. Now, in the first video lecture, we covered the band theory of solids, which was basically nothing but how the Banerjee bands of valence electrons get modified during crystallization process and how this band theory of solid can be used to classify solids into conductors, insulators and semiconductors. These were the topics we covered in our last video lecture, means video lecture 1. In this video lecture, we are going to talk only about semiconductors. We will keep aside the conductors and insulators and we are going to talk about only semiconductors. That means we are going to talk what are the different kind of semiconductors are, what are intrinsic semiconductors and extrinsic semiconductors. Sometimes the intrinsic semiconductor are called as pure semiconductor and extrinsic semiconductor are called as impure semiconductor. Why it is so? What are p-type semiconductor? What are n-type semiconductor? Now to begin with, let's classify the semiconductor material first. Now depending upon the origin, that means depending upon the fact from where you are getting the semiconductor material, the semiconductors can be divided into two types. One is called elementary semiconductor, one is called compound semiconductor. Now elementary semiconductors are those which are available in natural form, but that means you can get them directly from nature. You can mine them. And for example, silicon and germanium are natural semiconductors. You can get them directly from the nature. Whereas compound semiconductors are man-made semiconductors. That means they are made by human beings. How? By compounding different forms of metals. And these compound semiconductors are again can be divided into three types. One is called inorganic semiconductors, one is called organic semiconductors, one is called organic polymers. The examples of inorganic semiconductors are cadmium sulfide, gallium arsenide, etc. And nowadays, these inorganic semiconductors like cadmium sulfide, gallium arsenide, they are very much in demand. People are not very much using silicon and germanium, which we are getting as natural semiconductor directly from nature. And examples of organic semiconductors are anthracene, dot patholocyanines. Whereas organic polymers, examples of organic polymers are polypyrrole, polyaniline, polythiophene, like that. Now, depending upon the conduction process, semiconductors can be divided into two types. One is called intrinsic semiconductor, which is also called as pure semiconductor, and another is called extrinsic semiconductor, which is also called as impure semiconductor. Now we are going to discuss in detail about intrinsic semiconductors and extrinsic semiconductors. Now intrinsic semiconductors are also called as pure semiconductors because these are the purest form of semiconductor. That means there is no any impurity present in the semiconductor or there is no any defects present in the semiconductor. The examples are silicon and germanium, and you can get intrinsic semiconductor as single crystal. Single crystal in the sense there are only germanium atoms and the entire crystal is made up of only germanium or silicon atoms. Now let us discuss the process of electrical conduction in an intrinsic semiconductor. To learn that, let us consider a part of a germanium single crystal. This is a part of a germanium single crystal consisting of few germanium atoms which are placed at equal interval in their lattice points. Now, since the germanium atom has 4 valence electrons, each germanium atom will make a covalent bond with the nearby 4 germanium atoms to make a germanium crystal in the neutral form. So, these 4 electrons of germanium will form covalent bonds with the nearby 4 electrons of the germanium atoms, so that both the germanium atoms, this germanium atom and this and all germanium atoms will fulfill the octet rule and they will remain stable. Similar is the situation for silicon semiconductor also. Since silicon is also having 4 valence electrons, silicon will also form similar kind of bond structure. Now when you supply small amount of heat to this germanium crystal, what will happen? Some of the germanium covalent bonds will break and one electron from those 2 electrons will be excited by leaving that bond, by breaking that bond. Now when heat is supplied, this bond got broken and one electron of this bond has been excited to get freed after breaking this bond. Similarly, another bond can also break so that one electron will leave from the bond and get freed for the process of conduction. Now in this event of excitation of an electron by breaking a bond of the germanium crystal, 2 things happened. One free electron or some free electrons got generated as a result of breaking that bond. At the same time, some requirement of electron or deficiency of electrons also got generated. In this example, one deficiency of electron got generated at this place and another deficiency of electron got generated at this place. Now since everybody in nature wants to be in stable state, these 2 covalent bonds, this covalent bond and this covalent bond, they will try to fix this problem. How they will fix this problem? There are 2 ways. In one way, these deficiency of electrons, they will try to pull electrons from the nearby germanium atoms. For example, this deficiency of electron can try to pull either this one or this one, or this one or this one or this one, and this also will try to pull one nearby electron from the another atom like this. So in this process, see, this electron, this deficiency of electron pulled this electron to fulfill its octet rule. But at the same time, the deficiency of electron has been transferred from here to here. In the event making or pulling electron from this atom to this atom, the hole or the deficiency of electron has been transferred from here to here. This is one way of fulfilling this deficiency of electron. Another way of filling this deficiency of electron is that this deficiency of electron will try to pull one of those excited atoms back to this position to make this covalent bond intact again. So, as a whole, when you are supplying heat energy to a single crystal of germanium or silicon, one excitation process is happening in which electrons from the covalent bond of germaniums will be excited to make them free. At the same time, one deficiency of electrons will be generated at the same place, and these deficiency of electrons are called as holes. Now, due to this stability, this deficiency of electron will try to pull nearby electrons to fulfill their octet rule, or this deficiency of electrons will try to regain the excited electron back to fulfill their octet rule. And this process of regaining the excited electron back to their original position to fulfill the octet rule is called regeneration. So, in general, two processes are happening. One is called excitation of electron, one is called recombination of electrons. At this point, if you will supply some potential across this semiconducting material, suppose positive potential here, negative potential here, then what will happen? The excited electrons will be drifted towards the positive potential. Since electrons are negatively charged, this positive potential will pull them towards positive terminal. At the same time, these holes will be pulled or drifted towards the negative terminals. As a result, you will get a current in the external circuit in the opposite direction of movement of electron or in the same direction of electron. So, you will get a current flowing in this circuit. Now, we can study the same thing using band theory of solid. You know that according to band theory of solid, a semiconductor is a material which has two bands. One is called valence band, one is called conduction band, and all the valence band energy levels are completely filled and all the conduction band levels are completely empty. And the highest level of the energy level of the valence band is separated from the lowest level of the conduction band by an energy gap is called forbidden energy gap. In case of semiconductor, this forbidden energy gap is around 1 electron volt. Now, in this band picture, when you are supplying heat, electrons are getting excited from valence band to the conduction band. At the same time, they are leaving behind two deficiency of electrons or called as holes. These are called deficiency of electrons and holes, and these are the excited electrons. And the number of electrons in the conduction band will definitely be equal to the number of holes in the valence band. Now, some electrons, after getting excited to the conduction band, they won't be able to live there for long, and they will immediately come back to recombine with the holes to make the bond stable. This process is called recombination. Now, when you are supplying some potential to this kind of material or intrinsic semiconductor, both electrons and holes will take part in the process of conduction. And since the number of electrons and number of holes are exactly equal in case of semiconductor, they will contribute equally to the process of conduction. Here in this figure, these are valence electrons which are taking part in the bond formation. These are covalent bonds. These are broken covalent bonds. After electrons getting excited from the bonds, they are breaking. And these are free electrons. These are holes, and electrons are having negative charge and holes are having positive charge. Now the hole, which is a deficiency of electron, does not exist in nature, in reality. It is just a conception to make the analysis simpler. Otherwise, the deficiency of electron, we mathematically give a positive charge to it, and we mathematically represent a current flowing due to the movement of electrons. But the holes do not exist in reality, and they do not have any physical space. It's just a mathematical conception for making things simpler. Now let's have a recap. In recap, intrinsic semiconductor is a pure semiconductor, as we studied. You will get them in their pure form, single crystal form. The energy gap in the intrinsic semiconductor for silicon, the energy gap in silicon is 1.1 electron volt, and that in germanium is 0.74 electron volt. The total current, when you are supplying a potential across the intrinsic semiconductor, the total current in an intrinsic semiconductor is given as current due to electrons and current due to holes. Total current I is current due to electrons and current due to holes. IE is the current due to electron and IH is the current due to holes. Now in an intrinsic semiconductor, number of thermally generated electrons equals the number of holes. These thermally generated electrons, which are generated by supplying heat, is equal to the number of holes, as we saw in the earlier slide. The number of electrons is exactly equal to the number of holes. And the number, if Ni and Pi are the concentration of electrons per meter cube, if Ni and Pi are the concentration of electrons and holes respectively in a semiconductor, then their number is given by the formula Ni equals to Pi equals to e to the power minus Eg divided by kBt, where Ni is the concentration of electrons, intrinsic electrons, Pi is the concentration of holes, and this number is equal to number of electrons as well as number of holes, since they are same. Eg is the band gap energy. This band gap energy, its value is 1.1 electron volt in case of silicon and 0.7 electron volt in case of germanium. Kb is called Boltzmann constant, and T is the temperature at which you are finding out the concentration. Now electrons, since electrons and holes are equal in numbers in case of intrinsic semiconductor, the process of conduction in case of intrinsic semiconductor will be contributed equally by electrons and holes. The quantity Ni and Pi, either Ni or Pi, is referred as intrinsic carrier concentration. The number of electrons or the number of holes per meter cube of the semiconductor material or per centimeter cube of the semiconductor material is called intrinsic carrier concentrations. Now you studied the intrinsic semiconductor, where you found that the process of conduction is solely due to electrons and holes, where the number of electrons and number of holes are same, and both of them were generated thermally by supplying heat. This means what? This means the intrinsic semiconductors, the conduction process or the conductivity of an intrinsic semiconductor is largely dependent on temperature. If you are changing the temperature slightly, the number of electrons as well as the number of holes will change abruptly. Since the number of electrons and number of holes will change, the conductivity of the intrinsic semiconductor will also change abruptly with temperature. So, such a crystal whose conductivity is largely dependent on temperature cannot be used for device application more reliably, because if you have used this pure semiconductor for the device application and somehow the temperature is getting increased, then the semiconductor device will behave badly and you won't be able to trust on that device. And second problem with the intrinsic semiconductor is the number of electrons and holes that you can generate thermally is limited. That means the number of electrons and holes you will be able to generate thermally should be or will be capped by or will be limited by the maximum number of electrons or holes present in the crystal. You cannot increase the conductivity beyond a certain limit in case of an intrinsic semiconductor. Now, to avoid these 2 points means to eradicate this problem of limited conductivity and temperature dependence of the conductivity, people started making extrinsic semiconductors or pure semiconductors. These extrinsic semiconductors are made up from intrinsic semiconductors by doping them with some impurity. So, doping is a process in which we deliberately add a very small amount of impurity into an intrinsic semiconductor. These impurity atoms are called dopants, and the semiconductor containing the impurity is called impure semiconductor or extrinsic semiconductor. We will go in detail what are these extrinsic semiconductor or impure semiconductors. Now, the number of outer electrons in the dopant atom decides the type of doping. If the number of outer electrons in the dopant atom are 5, that means there are 5 valence electrons in the impurity atom, then that type of extrinsic semiconductor or that type of doping is called N type of doping. If the number of valence electrons are 3, that means if the dopant atom is a trivalent dopant atom, then that type of doping is called P type doping. Now, there are various methods or various processes of doping. One is a process in which we heat the single crystal of silicon or germanium in the presence of dopant atoms, those impure atoms, in vacuum. We keep the single crystal in vacuum and we heat that, and at the same time we will supply some dopant gas of dopant atoms, and they will be deposited layer by layer on the wafer or on the single crystal, and this process is called epitaxy. If you are interested, you will be able to, or you will be studying this process in detail in your higher classes of semiconductor material. This process is called epitaxy, where we heat a single crystal in the presence of dopant atoms, so that those dopant atoms or impurity atoms will be deposited layer by layer on the single crystal. Second method is adding some impurity in the molten state of semiconductor. We used to increase the temperature of the semiconductor to bring it to the molten state, and after that we add some impurity in the liquid form, and this process is called diffusion. After adding those impurity atoms in liquid form, they will be spreaded, they will be diffused inside the molten state of the dopant or of the single crystal, in a same way in which if you are putting a drop of ink in a glass of milk, the ink will be diffused slowly inside the milk. In the same process or similar process, they used to add impurity in the molten state of semiconductors. That process is called diffusion. Another process is called ion implantation, where they bombard or they incident very high energetic impurity atoms onto the semiconductor single crystal. There will be a semiconductor single crystal in the form of wafer. They will bring these dopant atoms, they will accelerate them with very high potential, and they will be bombarded onto the semiconductor single crystal to impose some impurity in the crystal. This process is called ion implantation. In this class we discussed about intrinsic semiconductor. What is an intrinsic semiconductor? What are the different behavior or how the conduction process happens in case of an intrinsic semiconductor, and how the conduction or conductivity of an intrinsic semiconductor increases or decreases by temperature, by increasing or decreasing temperature. Please note that the conductivity of an intrinsic semiconductor is 0 at absolute 0 degree temperature. Also, we studied how what is an extrinsic semiconductor and how an extrinsic semiconductor can be obtained by the process of doping. In the next class, we will discuss about the extrinsic semiconductors only. What are N-type semiconductor, what is P-type semiconductor, those things we will be discussing in the next class. Thank you.